Welcome to a deep dive into one of the greatest achievements in 20th century physics, the BCS theory of superconductivity. Superconductivity is a quantum phenomenon where materials conduct electricity with absolutely zero resistance below a critical temperature. Three brilliant physicists solved this 46-year-old puzzle in 1957. John Bardeen, Leon Cooper, and Robert Schrieffer worked together at the University of Illinois to develop what we now call BCS theory. Let's understand the puzzle that had stumped physicists for nearly half a century. In 1911, Dutch physicist Heineke Kamerlingh-Onnes discovered that Mercury's electrical resistance completely vanished below 4.2 Kelvin. The resistance drops sharply to zero at the critical temperature, a phenomenon that classical physics could not explain. Classical theories predicted that even at low temperatures, electrons should still scatter off impurities and lattice vibrations, producing some resistance. By the 1950s, experimentalists had accumulated three critical pieces of evidence. First, the heat capacity showed a discontinuous jump at the critical temperature, suggesting a phase transition. The specific heat jump follows this relation, where Cs is the superconducting heat capacity and Cn is the normal state value. The heat capacity shows a characteristic jump at T equals Tc, indicating that energy is suddenly needed to break Cooper pairs. Second, superconductors expel magnetic fields, a phenomenon called the Meissner effect. The magnetic penetration depth lambda varies with temperature according to this formula, diverging as T approaches Tc. Magnetic field lines are expelled from the superconductor interior, with field penetrating only a thin surface layer of depth lambda. Third, and most crucial, was the isotope effect discovered in 1950. The critical temperature depends on the isotope mass m with an exponent alpha approximately equal to 1/2. Here's the key question. Why would changing the atomic mass of the lattice ions affect the critical temperature? The answer is profound. The lattice vibrations, or phonons, must somehow be mediating the electron interactions. Heavier isotopes vibrate more slowly, changing the phonon spectrum and thus the effective electron-electron interaction strength. In 1956, Leon Cooper made a crucial discovery about electron behavior near the Fermi surface. Cooper proved that two electrons just above the filled Fermi sea can form a bound state through phonon-mediated attraction, no matter how weak. The binding energy of a Cooper pair is given by this expression, where omega d is the Debye frequency, n0 is the density of states, and v is the interaction strength. The mechanism works like this. The first electron polarizes the lattice, creating a region of positive charge that attracts a second electron. Two electrons exchange virtual phonons, creating an effective attraction that overcomes the direct Coulomb repulsion at low energies. The momentum range for pairing is given by omega d over versus f, which is much smaller than the Fermi momentum kf. For typical superconductors, the binding energy of a Cooper pair is about 1 millielectron volt, corresponding to temperatures of a few Kelvin. Bardeen and Schrieffer extended Cooper's idea to all electrons near the Fermi surface. The crucial insight was that it's not just one Cooper pair, but a coherent quantum state, where many pairs overlap and correlate. The BCS ground state wave function is this product over all momentum states k, with amplitudes uk and versus k, describing the probability of each state being empty or doubly occupied. The amplitudes satisfy this normalization condition, representing the quantum superposition of paired and unpaired electrons. In the BCS state, electrons form Cooper pairs with opposite momenta and opposite spins, creating a macroscopic quantum coherent state. How do we determine the optimal values of uk and versus k that minimize the ground state energy? We use the variational principle, minimizing the expectation value of the Hamiltonian with respect to these amplitudes. The most important result of BCS theory is the prediction of an energy gap. The quasi-particle energy Ek is given by the square root of xi k squared plus delta squared, where xi k is the energy relative to the Fermi level. The gap delta varies with temperature according to this hyperbolic tangent function vanishing at Tc and reaching its maximum at zero temperature. The gap decreases smoothly from its maximum at zero temperature and vanishes continuously at the critical temperature. The zero temperature gap is related to the critical temperature by this universal ratio, 2 delta 0 equals 3.52 times kBTC. For aluminum with a critical temperature of 1.2 Kelvin, the predicted gap is about 0.18 millielectron volts, in excellent agreement with experiment. The gap delta satisfies a remarkable self-consistent equation. This integral equation states that the gap is generated by the interaction V times the density of states, integrated over the phonon energy range. At zero temperature, the hyperbolic tangent becomes 1, and the equation simplifies considerably. We obtain this approximate solution for the zero temperature gap, showing exponential dependence on the coupling strength. This exponential form explains why superconductivity is a weak coupling phenomenon, requiring careful treatment beyond perturbation theory. BCS theory precisely predicts the discontinuity in heat capacity at Tc. The superconducting heat capacity has this exponential form at low temperatures, reflecting the thermal activation needed to break Cooper pairs across the gap. The red curve shows the BCS prediction for superconducting heat capacity, with exponential suppression below Tc and a jump at the transition matching the blue normal state curve. The ratio of the jump to the normal state heat capacity is predicted to be exactly 1.43, in remarkable agreement with experiments on many materials. This precise numerical prediction was one of the first confirmations of BCS theory's accuracy. BCS theory also correctly predicts how magnetic fields penetrate superconductors. The penetration depth follows this temperature dependence, diverging as T approaches Tc from below. The penetration depth increases gradually, then diverges rapidly near Tc, exactly as observed experimentally. The zero temperature penetration depth depends on the superfluid density Ns through this London equation form. For typical superconductors, lambda 0 ranges from 50 to 500 nanometers, defining the scale over which magnetic fields penetrate the surface. BCS theory provides a quantitative explanation for the isotope effect. Since Tc depends on the Debye frequency omega d, and omega d is proportional to m to the negative 1/2, we get the isotope effect. The Debye frequency scales as m to the negative 1/2, giving exactly alpha equals 1/2 for the isotope effect exponent. Experimental data points fall beautifully on the predicted inverse square root curve, confirming the phonon-mediated pairing mechanism. For mercury isotopes, the measured exponent is 0.50, in perfect agreement with the BCS prediction. BCS theory introduces another fundamental length scale, the coherence length. The BCS coherence length, xi0, equals h bar versus f divided by pi delta 0, representing the spatial extent of a Cooper pair. For conventional superconductors, the coherence length ranges from 100 to 1000 nanometers, much larger than the interatomic spacing. A single Cooper pair extends over a distance zn, containing millions of other overlapping pairs, creating the macroscopic quantum coherence. The ratio kappa equals lambda over Xi distinguishes type 1 from type 2 superconductors. Type 1 superconductors have kappa less than 1 over square root 2, while type 2 have kappa greater, leading to different magnetic behaviors. Electron tunneling experiments provided direct verification of the energy gap. Evers J. Evers tunneling experiments measured current through a thin insulating barrier between normal and superconducting metals. The tunneling current is proportional to this integral over the superconducting density of states Ns times the difference in Fermi functions. The superconducting density of states shows characteristic peaks at plus and minus delta with zero density inside the gap. These tunneling measurements directly confirmed the existence and magnitude of the BCS energy gap. BCS theory explains the maximum current a superconductor can carry. The depairing critical current density is roughly Ns EVF over 3, where Ns is the superfluid density. What happens when we try to push more current through a superconductor than this critical value? Above the critical current, the kinetic energy becomes large enough to break Cooper pairs, destroying the superconducting state. When current density is too high, pairs break apart and the material returns to the normal resistive state. For thin-film superconductors, critical current densities can reach 10 to 100 megaamperes per square centimeter. All superconducting properties show universal temperature dependence near Tc. The superfluid density decreases as ns0 times 1 minus T over Tc to the fourth power. Different properties show different but related temperature dependencies. Cyan shows superfluid density, magenta shows gap, and yellow shows critical field. The critical magnetic field varies as Hc0 times 1 minus T over Tc squared. Superconductivity is fundamentally a macroscopic quantum phenomenon. The superconducting order parameter is a complex field with magnitude and phase theta. The phase is coherent across the entire macroscopic sample, making superconductivity a true quantum phenomenon on everyday scales. The supercurrent is proportional to the gradient of the phase, connecting macroscopic current flow to quantum phase. The phase theta varies continuously around the superconductor, with phase gradients producing persistent currents. One of the most striking predictions is magnetic flux quantization. Magnetic flux through a superconducting ring is quantized in units of phi0 equals h over 2e, the flux quantum. Numerically, the flux quantum equals 2.07 times 10 to the negative 15 Weber, an incredibly small but measurable quantity. A single superconducting ring encloses a magnetic flux that is an integer multiple of phi0, illustrating quantum coherence on macroscopic scales.